Relational databases. Databases have been a staple of business computing for the very beginning of the digital era. In fact, the relational database was born in 1970 when E.F. Card, a researcher at IBM, wrote a paper outlining the process. Since then, relational databases have grown in popularity to become the standard. Relational databases use tables to store information. The standard fields and records in a table are represented as columns or attributes and rows or tuples, and all of the attributes stand in relation with each other. Relational databases are created using a special computing language known as Structured Query Language, or SQL. SQL is the foundation for all of the popular databases applications available today. From Access to IBM to Oracle. When a database is described as relational, it has been designed to conform, at least mostly, to a set of practices called the rules of normalization. For example, in a university you have students who take specific classes. Each student and a class has a number and a name. You could organize this information as shown in this table. But if you structure your data in this way and make certain changes to it, you'll have problems. For example, deleting all the students in the web design class will eliminate the class itself, or if you change the name of the Intro to Computers class to Computers for Beginners class, you need to change this record for each student in that class. Using the principle of relational databases, the student and class data can be restructured into two separate tables. This allows to easily find specific information. It also allows you to sort based on any field and generate reports that contain only certain fields from each record. By storing this information in another table, the database can create a single small table that can then be used for a variety of purposes by other tables in the database or for storing data that has to do with both tables, like a student's grade in a specific class. A typical large database, like the one a big website uses, such as Amazon, Takealot, or Wikipedia, will contain hundreds or thousands of relational tables all used together to quickly find the exact information needed at any given time. To sum it all up, the relational database model is made up of tables consisting of rows and columns. Each column has a name and a single data type. Multiple dimensions are represented by multiple tables which are joined to construct a multidimensional object or by multiple rows in a table. But relational databases only support the following data types: integers, floating points, character strings, data types, and currency. If it doesn't fit in one of the above, then it is a binary large object, or better known as a blob. Since the new world of information is all about blobs, like video and audio files, and developers cannot use blobs in a relational database, they started to use object-oriented databases. This, unlike relational databases, provides for data objects to store in one data structure, the data and the rules and ways about how the data can be accessed. It also allows for complex data types to be intermingled into one database. Even though object-oriented databases and relational databases have quite a lot of similarities, object-oriented databases is still not used as much since relational databases are more mature, more extensively tested, has already advanced amount of data in this format, and programmers know how to optimize it for high-speed retrieval.
Next up is object-oriented databases, commonly referred to as object database management systems. Unlike relational databases, object databases store objects rather than data such as integers, strings, or real numbers. These objects are then used in object-oriented languages such as C++, C#, and Java. The objects used in these languages primarily consist of attributes and methods. Attributes would be the characteristics of the objects and methods being the behavior. Object-oriented databases are best used for complex data and/or complex data relationships. Now we will compare object-oriented databases to other types of databases found in today's world. Relational databases store data in tables that are two-dimensional, either in rows or columns. Each table has a primary key, for example, ID number, social security number, which is then used to associate one table with another. NoSQL is a mechanism for storage and retrieval of data. It, however, has finer control over availability but lacks true ACID transactions. Data warehouses are used for reporting and data analysis and act as a central repository for all integrated data.
Hi, today I'm going to be speaking about NoSQL databases. As you can see in this first slide, there's quite a few companies that offer NoSQL databases, including Basho and Oracle NoSQL database. Firstly, it's categorized by scalability, which basically means how easily a database can grow with the expansion of a business. Secondly, NoSQL database deals with a high volume of data. It also has a high fault tolerance, and because it is found in the cloud, it is location independent. There are other things that are applicable to a NoSQL database, such as a NoSchema database, and it is a NoSchema database, and it has an ad hoc organization structure. There are 4 types of NoSQL databases. The first one being a key value store, a column store, document database, and a graph database. In this image on the right, we can see that the conventional SQL databases, such as the relational one and the analytical OLAP database, are much more structured and rigid than the non-SQL databases. Now, the key value store in this case consists of just a key and a value. The index key is unique to each collection, such as Arvind is then a type student age 20 who likes to play cricket. The column store, on the other hand, allows for high performance and scalability. It consists of 3 elements: a unique name, a value, these are both values, and usually it has a timestamp following it. A document database is designed for storing, retrieving, and managing document-oriented info. Each document also is assigned a unique key, such as beer 1429. A graph database is usually used when there is an undetermined number of relations between elements in a data. Now, comparing the NoSQL databases, depending on the company that you're trying to run or the business you're trying to run, that depends on which data model you want to use, because each one has different attributes and different performance keys, such as one is better in performance rather than scalability or flexibility. Advantages of NoSQL databases is high data velocity, data variety, data volume, and data complexity. Now, fault-tolerant NoSQL databases is there because it uses a distributed architecture that ensures data is always available and recoverable. NoSQL databases are distributed in the cloud, which provides continuous availability from multiple locations. There's never a need to take the database down when you're updating it or editing it. It's constantly in use and accessible. It is also location independence, another thing that comes with being in the cloud. You can have input-output operations from any location, which can be architected using relational databases, but that requires a lot of labor and a lot of skill and knowledge to do. It's a much cheaper alternative and more economical to go for the NoSQL. There's also modern transactional capabilities that come with NoSQL, unlike relational databases which use the ACID principle: atomicity, consistency, isolation, and durability. The NoSQL uses a cap theorem, which basically means that the system can have 2 of 3 desirable properties, either consistency, availability, or tolerance to network partitions. Flexible data. NoSQL databases are schema-less, so it accepts all types of data rather than in a relational database that relies on a predefined schema, which means it's much better for today's companies and businesses.
Greetings, fellow human beings. Today we will be having a little slideshow on the data warehouse. In this session, we will look at what is a data warehouse. Will cover the following: what a data warehouse is, a little comparison between the NoSQL database and the data warehouse. We will look at online transaction processing system versus data warehouse environments, data warehouse architectures, and that's about it. Let's get started. So we'll start with what is a data warehouse. There are a few descriptions or definitions around, but I've chosen a short one and a more detailed one to give you a better grasp of the concept. The short description is: a data warehouse is a copy of transaction data specifically structured for query and analysis. The more detailed definition: a data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data in support of management's decision-making process. In that definition lies 4 key words: subject-orientated, integrated, time-variant, and non-volatile. So what does this all mean?
Well, subject orientated. This means that a data warehouse can be used to analyze a particular subject area. An example of this is sales can be a particular subject. Integrated. This says that a data warehouse integrates data from multiple data sources. An example of this would be source A and source B may have different ways of identifying a product, but in a data warehouse, there will be only a single way of identifying a product. Then we move on to time variant. With this, you sort of know that historical data is kept in a data warehouse. That's what it's all about here. So you can pretty much go back, for example, one can retrieve data for 3 months, 6 months, even 12 months or older than that from the data warehouse. Now, this contrasts with a transaction system, where often only the most recent data is kept. And an example of this is a transaction system may hold the most recent address of a customer, where a data warehouse can hold all addresses associated with a customer. The last keyword is non-volatile. This says that once data is in the data warehouse, it will not change. So historical data in a data warehouse should never be altered. Moving on to some of the characteristics, we will just touch on about 6 of them here. Number 1, data is structured for simplicity of access and high-speed query performance. Number 2, end users are time sensitive and desire speed of thought response times. Number 3, large amounts of historical data are used. Number 4, queries often retrieve large amounts of data, perhaps many thousands of rows. Number 5, both predefined and ad hoc queries are common. Number 6, the last one, the data load involves multiple sources and transformations. We'll move on to some of the benefits of data warehousing. One is that it can congregate data from multiple sources into a single database. And so a single query engine can be used to present data. Another benefit is it mitigates the problem of database isolation, level lock, contention in transaction processing systems caused by attempts to run large, long-running analysis queries in transaction processing databases. Another benefit is it maintains data history even if the source transaction systems do not. You are able to integrate data from multiple source systems, enabling a central view across the enterprise. The benefit is always valuable, but particularly so when the organization has grown by a merger. The last benefit that we'll look at is it improves data quality by providing consistent codes and descriptions, flagging or even fixing bad data. Now we'll just look at a little comparison or what similarities the NoSQL database has against the data warehouse. They don't really have much in common. The main similarity is that any two data warehouses can have very different philosophies or conventions, just like any two NoSQL systems can be nearly unrelated. The only concept they share is that they are both used to analyze large amounts of data. With the NoSQL solutions, they usually manage relatively limited schemas with large cardinality in few entities, while data warehouses typically have lots of facts and dimensions, or lots of entities in third normal form model. Data warehouse systems usually manage multiple lines of business and attempt to combine the data. You see, data warehouse systems, they typically have reporting abilities in SQL, which allows you to access all the data in a standard way. With NoSQL systems, they are typically more code-based, for instance, an application like MapReduce. Now we will look at the online transaction processing system versus the different data warehouse environments. There's a little diagram here that shows you the comparison between the two different systems. There are quite big differences between the OLTP system and a data warehouse. The one major difference between the types of the systems is that data warehouses are not exclusively in third normal form, a type of data normalization common in OLTP environments. Data warehouses and OLTP systems have very different requirements. Here are some of the examples of difference between typical data warehouses and OLTP systems. We look at workload. So data warehouses are designed to accommodate ad hoc queries and data analysis. You might not know the workload of your data warehouse in advance, so a data warehouse should be optimized to perform well for a wide variety of possible query and analytical operations. OLTP systems support only predefined operations. Your applications might be specifically tuned or designed to support only these operations. Data modification. A data warehouse is updated on a regular basis by the ETL process using bulk data modification techniques. The end users of a data warehouse do not directly update the data warehouse except when using analytical tools such as data mining to make predictions with associated probabilities, assign customers to market segments, and develop customer profiles. In OLTP systems, end users routinely issue individual data modification statements to the database. The OLTP database is always up to date and reflects the current state of each business transaction. Another difference is the schema design. Data warehouses often use partially denormalized schemas to optimize query and analytical performance. OLTP systems often use fully normalized schemas to optimize update, insert, delete performance, and to guarantee data consistency. Another difference is typical operations. A typical data warehouse query scans thousands or millions of rows. Example, find the total sales for all customers last month. The typical OLTP operation accesses only a handful of records. For example, retrieve the current order for this customer. Historical data, this is another difference. Data warehouses usually store many months or years of data. This is to support historical analysis and reporting. In OLTP systems, usually store data from only a few weeks or months. The OLTP system stores only historical data as needed to successfully meet the requirements of the current transaction. We'll touch on a bit of the architectures now. Basically, there's 3 common architectures, and they vary depending upon specifics of an organization. So the first one is the data warehouse architecture, which is basic. The second one is the architecture with a staging area. And the last one, an architecture with a staging area and data marts. Okay, so we'll start with the basic architecture. You can see on the right-hand side, there's a bit of a diagram that shows you a little summary of the architecture for the data warehouse. The end users directly access the data delivered from several source systems through the data warehouse. That's basically what it shows you in there. So in this figure, the metadata and raw data of a traditional OLTP system is present, as is an additional type of data, summary data. Summaries are a mechanism to pre-compute common expensive long-running operations for sub-second data retrieval. For example, a typical data warehouse query is to retrieve something such as August sales. A summary in an Oracle database is called a materialized view. The consolidated storage of the raw data as the center of your data warehousing architecture is often referred to as an enterprise data warehouse. An enterprise data warehouse provides a 360-degree view into the business of an organization by holding all relevant business information in the most detailed format. The next architecture is the one with the staging area. The diagram here shows you the architecture of the data warehouse, and in the diagram you can see that you must clean and process your operational data before putting it into the warehouse. That's what this shows you. You can do this programmatically, although most data warehouses use a staging area instead. A staging area simplifies data cleansing and consolidation for operational data coming from multiple source systems, especially for enterprise data warehouses where all relevant information of an enterprise is consolidated.